Today we are going to be talking about the torque speed characteristics of separately excited DC motor. As we know that separately excited DC motor is a type of a DC motor. Also, we have got other types of DC motor which comprise of the series DC motor, the shunt DC motor, the compound DC motor, and of course the one we are discussing right now, which is the separately excited DC motor. Without wasting much of the time, let us just draw what a separately excited DC motor is. Yes, we have got the back EMF right here, which will be acting in the opposite direction. We have got the armature current. This is the armature current, and we have got the armature resistance, taking the Kirchhoff's voltage law, which states that this is the Kirchhoff's voltage law. We are just taking one of the loops of this of circuit diagram. This one is our voltage power supply, which is going to be voltage going right here. We are going to see that it's going to be IA RA plus EB, where EB is the back EMF. But we can see that this equation of ours is not looking that sexy. It's not looking that sexy. How do we make it sexy? How do we make it sexy? We are just going to rearrange our terms. We are going to get EB plus IA RA. Nothing has changed. Nothing has changed. We are going to be getting our first equation. This is our first equation. This, you can see that it's sexy. It's a sexy looking It's a sexy looking equation. Let me just erase this so that we continue on moving. We continue on moving. So we now have our first equation, V, which is equals to EB plus IA RA. But we know that let me just erase the B. We know that E is equals to NP phi Z upon 60A. Upon 60A. This is our equation Our equation 2, where this N is the speed. N is the speed. P is the number of poles. P is the number of poles. Phi is the flask. Phi is the flask. Z is the number of the armature conductors. And A is the number of parallel paths. But we know that NS is equals to N over 60. Where N is the speed per second. N is the speed per second, but we want speed in radians. So we are going to take omega S, which is equals to 2 pi N 2 pi NS. But NS here is this one. We are going to be substituting this one into our equation. So we are going to erase this and put that N over 60. This will be This will be our new equation. Our new equation. Now this is the omega S. This is the speed in radians. So we are going to make this speed, which is revolutions per minute, we are going to make it the subject of the formula. How do we make it the subject of the formula? We just say 60 omega S over 2 pi is equals to Is equals to N. This is the equation Our equation 3. This is our equation 3. And we are going to take this, we are going to put equation 3 into Into equation 2. Let me just rub it here. Let me just rub this off. So our equation 2 is going to become E is equals to, we substitute S, we put We put this 60 omega S P phi Z over Over 60A. over 60A. Over 60A, you can see that this cancels each other. This cancels each other. We are left with E is equals to, omega S P phi Z over what? Over A. Something like this. Something like this. Something like this. So over 2 pi, over 2 pi. I had forgotten to put the 2 pi. Over what? Over 2 pi. So now we can see that here, as we arrange this equation, E is equals to omega S phi P Z over 2 pi A. Something like this. You can see that this is a constant. Let us just equate it to a constant what? A constant Ke. Constant Ke. So our E is equals to K omega S phi. Let me just put it onto the top. From these two equations, it can be denoted that E is equals to omega S P phi Z over what? Over 2 pi. So we can rearrange this as E is equals to omega S phi P Z over 2 pi. This is a constant Ke. This is a constant, this is a constant, this is a constant, this is a constant. We can just redefine it, give it a new constant. So E will be equal to Ke omega S phi. This is our equation 3. So we have not yet described the torque speed characteristics of separately excited DC motor, but for the sake of our video, we are going to end it right here, and we are going to continue it into the next equation. So this is part 1. Part 1. We are going to be going for part 2.